Good afternoon, everyone, and welcome to the Science Club, the last one before the summer break. I'm Alessandra Picella, and I'm in charge of the Science and Technology Office at the Embassy of Switzerland in Seoul, and we are part of the SwissNext network. We organized the Science Club generally at the embassy, but because of COVID, we switched to the digital version, which actually offers us also the opportunity to be connected with our with our partners in Switzerland. So it's a pleasure to welcome you here. Today, today's Science Club will start soon, and we are going to have two speakers. We choose Professor Dong Ki-yoon and Professor Lucio Isa because the two of them apply for kind of a co-founded program from the Swiss National Science Foundation and National Research Foundation in Korea, and their project was granted at the end of 2019. And they will start soon the cooperation on this project, which has been a bit delayed because of the COVID pandemic. So I'd like to introduce first Professor Dong Ki-yoon, and I ask him to turn on his video and also say hello to our participants in order to be seen from them.
Hello.
Hello, Donkey. So Professor Dong Ki-yoon is KAIST Associate Professor of Chemistry, and since the beginning of his career as a faculty member in KAIST about 9 years ago, he has been actively engaged in research projects in the field of soft matters. He also has continued to integrate new and innovative concepts and thoughts in his research group. And the research topic in his group can be categorized as follows: nano and microfabrication, stimuli responsive supramolecules, biopolymers for partnering application, LC organic electronics. I'm gonna now introduce the second speaker of today, Lucio Isa. So Lucio, please turn on your camera and say hello also to our participants.
Hi everyone, good morning or good evening, depending where you are.
So Lucio is Associate Professor of Soft Materials and Interfaces at ETH Zurich, and accounts international experiences in Italy, his origin country, Scotland and Switzerland. He has a long history of successful fellowship under European and Swiss programs, which led him to his current position. He is also co-founder of Swiss Soft Days, an initiative aimed at creating a national network of scientists working in soft matter in Switzerland. Before giving the word to our first speaker, I would like to ask the participants to write down their questions during the presentation by using the Q&A section in this in Zoom, and to use instead the chat section just if there is any technical issue, any technical problem. So at the end of the two presentations, for practical reasons, I will ask the questions to the speaker for you. In case we will not have enough time to answer all the questions, you will receive the answer in a written form later. So I kindly ask Professor Dong Ki-yoon to start his presentation. So my colleague now, she stops sharing this screen. In this way, we can switch to the screen of Professor Yoon.
Okay.
Please, Professor Yoon, you can share.
Can you see that?
Yes.
Can I start from now?
Yes, you can start.
Okay, thank you for kind introduction. This is Dong Ki-yoon in KAIST. Today I'm going to talk about the defects of liquid crystal and their phase transition. As shown in this video, this large defect in the nematic phase, high temperature phase, is changed to the small ones as shown here. So I'll show how this happens in the liquid crystal phases, which will be collaborated with Professor Isa. So in today's talk, I'm gonna introduce first about the liquid crystal and orientation control of the LC molecules. Then I'll move to the defect in the LC phases. And then I'll talk about the thermal phase transition of defects in the alpha phases, and I'll introduce the strategy how to work together with Professor Isa, and I'll conclude today's talk. When you Google liquid crystal, you'll find these beautiful images, including this rod schemes. So each rod means some molecules. So rod represents the small molecular weight liquid crystal, and when you see this one, you'll see how the defect structures are changed depending on the temperature, which was done by our group in 2017, I think. First of all, liquid crystal is not a material, but the phase in the middle of the crystalline solid and isotropic liquid. It has orientational order as shown here, but does not have the positional order like crystalline solid. And this nematic and smectic A phase are two representative the liquid crystal phases. In smectic A phase, not like a nematic phase, it has a layered structure. I show the details about it. Once again, this rod, previously I showed the rods. Each rod represents single molecule or these two molecules as shown here. Especially in this case, we used ACB. Here A means octyl, C here means cyano, B means a bipanel. So ACB molecule will be used in today's talk. Nematic phase. When you visit the lake or river, you will see the fish swimming against the stream as shown here. Like this, the nematic phase, its molecules are arranged like this way with some orientation, direct N. Smectic A phase, on the contrary, it has some layers in between the molecules, just like bookshelf structure. So sometimes it is called the bookshelf structure, as shown here. It has some imaginary or real the layers in between the molecules, and it has short range order compared with this nematic phase. How to control the orientation of liquid crystal molecule? It is extremely easy when we use the cleaned glasses and silicon wafers or water phase. The molecules will be planar aligned like this way. And homeotropic or perpendicular alignment can be obtained when you use the liquid crystal air interface. For example, you can imagine the substrate, glass or water. Then the liquid crystal droplet can be placed on the substrate. Then on the bottom, the molecules will be arranged like this way. And near the alpha air interface, the molecules will be arranged like this way. So this antagonistic condition can make this tangential alignment of the liquid crystal molecule, which will be used to make defect in the liquid crystal phase. So singularity can be found in the universe as shown here. So for example, here black hole can be made like this way. So here the planar alignment can be found here, and the perpendicularly alignment can be found here. So this is kind of direct field of liquid crystal, and this antagonist condition can make singularity, which is the defect in the liquid crystal phase, which can be found in the eye of typhoon or hurricane, or in bathroom, or even in toilet. One thing you notice here is do not throw the clownfish in the toilet when you flush it. Anyway, it looks like that one, the topological defect or singularity in the liquid crystal phase, as shown here in the nematic phase and smectic phase. The singularity or defect in the nematic phase is a little bit bigger compared with that one with the same scale. So I show the details about the defect structure of this from this slide. One thing you notice here is you will see blue and yellow colors. Blue here means the molecules are arranged like this way. And yellow means molecules are arranged like this way. So here, the molecules arranged here like this way. So each blue and yellow domains means this and that arrangement. So blue and yellow, from these colors, you can determine the orientation of liquid crystal. Once again, this surface orientation can be obtained using different substrate. For example, this is top view of the top defect of the in the nematic phase, and this is side view. This is top, and this is side view. And on the bottom, once again, this is obtained on the water. You can see this field, which means the molecules or rods are arranged like this way. This is near the air healthy interface. So here, the molecules are arranged like this way. And this is bottom view, or this one. So here, you can expect molecules are arranged like this way. This is called the +1 defect. So strength, here, this is S. S equals to rotation of the molecule over 360 degrees, which means here the molecules are rotated 360, so which is +1. But in this case, molecules are rotated like this, 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 and that way. So minus 660 over 660 equals to -1. So it is called the -1 defect, and this is called +1 defect. And this is the field of the liquid crystal molecules. Once again, we use the ACB molecule, and it has nematic phase at high temperature, and it has smectic phase at relatively low temperature. And with the perspective view, you'll see imaginary some defect core, and on the bottom, the molecules are arranged like this, and on the contrary, this, the molecules are arranged perpendicular near the air interface, and this is the cross-section view. It is called the Boojum defect because it looks like a Boojum tree. So as shown here, Boojum tree looks like the branches are arranged like this way, and it is just like this one. So it is called the Boojum defect in the nematic phase. In the smectic phase, as I mentioned, it has short ordering compared with the nematic phase. So smaller defect can be found, but still you'll see the different orientation on the bottom, planar alignment, and the perpendicular alignment on near the air interface as shown here. This tangential alignment can make this defect structure in large area. So I'll call this one focal conic defect in the nematic phase from now on. Let's see the thermal phase transition of defect structure in the nematic phase, from the nematic phase to the smectic A phase, as shown here. This Boojum defect will be changed to this focal conic domain on the water surface. Normally, people use this solid substrate, but in this case, even though the planar anchoring condition is used, the surface anchoring is too strong to see the freely moving the defect structure. So once this structure is changed to the focal conic domain, they do not move. On water, on slippery water surface, they can move very freely. For example, as shown here, individual focal conic domain can float on the water surface. So that's why we could see the thermal phase transition of defect directly with the optical microscope. It's just like oil on the water. So they can move freely on water surface. This is our strategy to see the thermal phase transition of the defect structure. So once again, this is projection view, perspective view, and this is cross-section view. On the bottom, you'll see +1 defect. And when this is also called +1 convergent defect. Sometimes we can see this directional one. This is called +1 divergent defect. Even though it shows the same +1 sign, but it does not have same orientation. But -1 does not have convergent or divergent one. As shown here, this yellow means molecules are arranged like this and that way, but still we can determine the direct field goes like that way. It is called +1 divergent defect, and on the contrary, it is made together with one point. It is called +1 convergent defect. It just looked like a -1 defect in the cross-section view, but from top view, we'll see the difference between -1 and +1 convergent defect. And for example, as shown here, this is the +1 divergent defect, this one. So, and final, you'll see this Maltese cross pattern. So the direct field goes this way with +1 sign. So with this experiment, we can determine which one is +1 or -1, and the transition from nematic phase, the defect structure from the nematic phase to the smaller focal conic domain in the nematic phase as shown here. So once again, this is +1, the divergent defect. So from this and that one, smaller one, we could see some stripe patterns. Once again, this is the arrangement of the molecule here, and here the molecules are arranged like this way. So with stripe pattern still, you can see how the molecules are arranged with blue and yellow colors. How to work together? Recently, very recently, with this paper, we recognized this convergent Boojum and divergent Boojum with +1C and +1D, though we knew -1 defect existed in the nematic phase. And the cross-section view of this and that one is same, but on top view, as shown here, which is not same. So arrangement is totally different, but the direction is different. So from this, we had an idea to control the orientation or to generate +1C or +1D or -1 defect by controlling this, by treat surface of the nanoparticle, microparticle as shown here. With the homeotropic anchoring, the molecules will be arranged like this way, but plane anchoring, on the plane anchoring, the molecules should be arranged like this way. And particle can be float on in the interface between LC and water surface. And from here, the defect structure should be controlled. So for example, with this preliminary result, we could not control it, but we could expect this orientation, +1D or +1C Boojum to that the focal conic domains. But Professor Isa is expert to control the particles in large area with topographic pattern. For example, as shown here, this can be a planar anchored particle, and this is the homeotropically controlled particle. Then we can we can imagine how to arrange the molecules near this topographic patterns. Based on this idea, we expect to control or address the defect cores, which can be used in patterning application or optics in the near future. For this, we visit his lab like 5 months ago when the COVID-19 was not so serious, but now it is serious. So that's why he did not come to our group, sadly. But hopefully we can work together closely in the future. Once it is solved, I think, as shown in this galaxy's fusion, as shown here, +1, when +1 defect and -1 defect meet together, you can still imagine the molecules are arranged like this and that way, right? But when they meet together to make 0, which is the minimum condition, the global minima in free energy, then you will see all the universe or all the molecules change to have the uniaxial alignment that's shown here, and which will be a clue to solve this kind of galaxy fusion, hopefully. And previous work was collaborated with Professor Daniel Bella in UC Mercy. And this work was initiated with this guy, Minjun Kim. It is followed, the work was followed by the Aram Sao. Now they are left. And these 4 guys are involved in this project. And thank you for your kind attention. And if you have any question, you can visit our home or you can email me with this email address.
Thanks a lot. Thanks a lot, Professor Yoon. I was really glad to watch your presentation because I went a bit back to my past because my master was focused on liquid crystals, and actually I was working on the 8CB and 5CB and different microscopy, yeah, it has been really interesting. So now I kindly ask to people interested in asking questions to Professor Yoon to write them in the Q&A session, but obviously indicating that the questions are for Professor Yoon. And in the meantime, we pass to the second presentation. So Professor Isa, floor is yours.
Okay, thank you very much. You probably see me now. Let me just share my screen.
I can see.
Yeah,
we see you, but not the screen yet.
Yeah, just a second.
Yeah, great. Now we see it.
Should come, right?
You should go now, yeah, full screen. And
full screen, you got it now, okay.
Now we see the presenter view.
Let's try this.
Yes, now it's good.
Okay, great.
Great.
So yeah, again, hi again from my side, and it's a pleasure to follow up with our presentation after the excellent presentation that our friend Professor Yoon gave you. So where you really went into some details in explaining the type of materials that we are interested in using. And towards the end of his presentation, he showed you how one can use colloidal particles to direct the formation of liquid crystalline defects. And towards the end of my presentation, I will go back to that point and see into some little bit more detail what kind of work we plan to do together, especially towards the initial phases of this collaboration, which I'm very happy that we can have even in these difficult conditions. And so before I go to that final point, I would like to discuss with you some recent technology that we have developed in our group to fabricate this type of very regular and very well controlled patterns of microparticles onto a substrate, with the idea that starting from the presentation of Professor Yoon's, you can see that each of these particles then can act as a nucleation point for a liquid crystalline defect. And in particular, I will show you how we can form those patterns by using capillary forces. But so before going to the details of that, I just wanted to give you a very brief introduction of sort of the motivation that one can have for the integration of multiple materials at the micron and nanoscale. So there's a broad range of different applications where it's really required to be able to place materials or let's say structural units or building blocks of the materials that have dimensions they are in the micron or submicron scale in very specific locations. And that typically has to do with our intentions to create hybrid devices basically at a small scale. So for instance, if we think about biosensing platforms, we would like to integrate biomolecules in specific positions onto for instance, a sensing chip. And so the question is that how do we integrate together materials that are so different in nature, say a metallic based or a semiconductor based chip with biomolecules. There are other applications, for instance, in microelectronics where you would like to use, for instance, individual nanowires as elements of circuitry. And again, here the question is, how do you put a nanowire that you typically synthesize using wet synthesis approaches into a device that you may pattern using standard lithographic techniques? So here you have to combine together materials that are fabricated in a different way and to still be able to retain the capability of placing all the components in the positions where you want them to be. There are other instances where, for instance, you would like to combine together two materials to fabricate what is often called heteronanostructures, where you take, for instance, in this case, a plasmonic nanoparticle and another nanoparticle that has a second harmonic generation optical properties, and you want to place them very close to one another with specific orientations to one another, because it's only the combination of these two materials combined at the nanoscale that sort of gives you the final optical property that you would like to do, that you would like to have, excuse me. And very often in our group, we are working on a field that I will not have time to cover today, which is the field of active materials. And in this case, what we consider by active materials are essentially colloidal particles, so micro nanoscale objects that are composed of compartments that are made of different materials. And it's this asymmetric composition that actually makes it possible for these particles to be actuated in an external field and act, for instance, as you see in this representation, as microscale machines capable of collecting a cargo, transport a cargo, and deliver a cargo, where the integration of two materials or more than two materials at a small scale really is the key to be able to enable the functionality of this. So the question is that, how do we do this? How do we integrate together different materials at that length scale? And the conventional top-down methods, like lithographical methods that are commonly used in the microelectronic industry do not work, essentially, because you have a limited choice of materials that you can integrate, and you have a limited choice in the flexibility of how you can integrate these materials together. And very often we have, let's say, extraordinary quality of micro nanoscale materials that can be synthesized via wet synthesis methods, and then we would like to integrate those with pre-existing platforms. And so top-down methods are not workable in that sense, and what we need to resort to is what are called bottom-up methods. So where we basically assemble together particles that are preformed from solution onto the positions where we would like to have them on our final device, on our final material. And so the strategy that we choose to do this is what is called directed assembly, which essentially means that we take colloidal particles and we direct their assembly into specific positions. In this specific case, I'm going to show you in a moment, using capillary forces. So I know that also Korea is a country where there's a lot of people that like to drink coffee. So maybe many of you have seen this phenomenon happening on their desk if they are as messy as I am. So if you spill some coffee on your desk and you let the stain of coffee dry, then you recover what is typically called the coffee ring effect. So what you see here, this is an example of essentially a coffee drop evaporating on a table. So in this case, it's a suspension of colloidal particles, very similar to what you have in your coffee, where you have this fine powder that actually is what gives coffee the color and the taste. And you see that as this droplet is spinned, the edge of the droplet is spinned onto the surface of the underlying substrate, say the table, then you see an accumulation of particles towards the edge of that evaporating droplet. And this is a zoomed in version of what is happening over there. Essentially what is happening is that as the water evaporates faster at the edge of the droplet compared to the center of the droplet, you have an evaporative flux that brings liquid towards the edge of the droplet and then brings particles with it. So this causes the accumulation of particles at the edge of the droplet, which after all the liquid has evaporated gives you this characteristic ring shape pattern of the stain that you leave onto the table. And essentially what we use for our assembly strategies, as I will show you in a moment, is a controlled version of the coffee ring effect, where instead of having a droplet that is simply evaporating and not moving, what we have a situation where we have an evaporating droplet that is confined between two surfaces. One is a topographical template. So this is a silicon elastomer into which by nanofabrication and microfabrication techniques, we can pattern small cavities that we call traps. And then this droplet of a colloidal suspension is sandwiched between this template with the traps and a substrate that is then moved at a controlled speed. Evaporation of the droplet from the front causes the accumulation of particles over here, as you've seen in the movie representing the coffee stain evaporation. And this dense region of particles, which we call the accumulation zone, is where capillary forces are going to push individual particles inside the traps. And as the droplet is moving over the pattern, then you leave a controlled number of particles inside each of these traps. So what you see down here is a microscopy image. It's a real movie of a real-time assembly of these colloidal particles onto a PDMS template. Each of these little rectangles that you see down here is a rectangle that has about 2 by 1 micron lateral dimensions and a depth of about ½ micron. And then we're dragging a suspension of colloidal particles, which have 1 micron in diameter, over that template. This whitish tinge that you see over here corresponds to the accumulation zone of particles close to the meniscus edge. And then you see that as the droplet is moving over, you have this really well-controlled unzipping of the meniscus, where as the droplet moves over the traps, each individual trap is filled by a single particle by a downward capillary force. So this technique, we call it capillary assembly, and is a way to direct the placement of colloidal particles in specific positions onto a substrate by means of capillary forces through the mechanism that I just discussed with you. So if one does this type of assembly in a controlled way, then we have two possible conditions, and this is what our group has been working on quite a bit in recent years. So we can have the situation where the trap has a depth that is approximately the radius of the particle, or we can be in a situation where the trap has a depth that is approximately the diameter of the particle. In this case, this is the easiest case. As we move with the meniscus over the traps, then the traps are completely filled. So all of the available space in the traps is filled by the colloidal suspension. So in this case, we can place 2 colloidal particles inside a single trap with a single motion of the droplet over the template. And this is an SEM image that shows that we have a very high degree of filling each of these traps with a couple, with a pair of particles. While instead, if the trap is a little bit shallower, then what we observe is that systematically only 1 particle is assembled inside each of these traps. The details of this require more time than what I can have to explain this to you today, but essentially what happens in this case is that the trap is filled by 2 particles, and the capillary force acts on a particle at the, let's say, entrance of the trap, which pushes onto the particle at the back, and the particle at the back rolls out. And so in the end, as the meniscus moves over, you leave only 1 particle in the trap. So if you do this in a controlled way, as you can see, you can place individual particles into larger traps by moving the droplet over those particles, which then gives us the possibility to backfill the available space by a second particle type. And this is what also Professor Yun was hinting to in his presentation. So this, in fact, is the crucial point of this technique, is that we first have deposited, in this case, blue particles inside the trap. And the adhesion between the particles and the template is very strong due to van der Waals forces, so that when we come with a second droplet, in this case of red particles, the blue particles that we have initially assembled do not leave the traps into which were initially placed. And then we can come with the second droplet and then backfill the available space next to the blue particle using red particles. And so this is for us a very important step, especially in the directions of the collaboration that was previously announced, because it means that we now have the possibility of placing different particles, for instance, with different surface chemistries, in specific locations relative to one another onto a template, which is the starting point for the control generation, for instance, of defects with different anchoring conditions, as it was previously beautifully described. So just to give you an idea, essentially this technique makes it possible for us to decouple completely the geometry of these colloidal patterns that we make from their material composition. And this is thanks to the combination of these, of the existence of these topographical traps, of which we can control the shape and which define the final shape of the local clusters of colloidal particles, from their material composition, which we then control by controlling the sequence of the deposition steps. So we can have, for instance, 3 deposition steps with 3 different particles, which then give rise to a linear sequence of 3 different particles, one after the other. If we change the geometry of the traps, the same 3 particles can be assembled in a triangular geometry. Or we can have much more complex geometries. For instance, we can have L shapes, we can have long chains with a different, let's say, head group. And the beauty of this method is it really allows us to mix together a broad range of different materials, because the drivers for the assembly is not any specific chemistry of the particles, but the driver of the assembly are capillary forces. So as long as the particles can be suspended in water, we can place next to one another particles with different surface charges, for instance, particles made out of organic or inorganic materials, and even metallic nanoparticles in that respect. So the idea here is to use this technique to pattern the defects, I will show you in a moment. And for many of the projects that we do in our group, we then can also link these particles together, typically by thermal sintering. We can remove them from the template and we can have them in suspension. And that's a lot of the work that we do in our group is actually connected to the production of these anisotropic colloidal particles, of which we are then interested in studying the active motion, as I was very briefly discussing at the beginning. But in the framework of the project that we're working together with our Korean collaborators, the idea is to use these patterns from the template in which they are fabricated as a way to nucleate defects in specific positions. And so here we started to look and to work onto some specific designs to reach the results that Professor Yoon showed you in the previous talk, where we have the possibility now to control areas on a chip where we can assemble colloidal particles of similar or different anchoring properties at specific positions. And so this is a very schematic design of how the chip is going to look like. And the beauty of our technique is that we can then very carefully control the size of these particles that are generating the defects, the surface chemistry of the particles that are generating these defects, and the relative arrangements of these particles with respect to one another. And so here, for instance, we can tune independently the size of the particles that we use for the creation of the defects and their distance, as well as the local arrangements. We can arrange them into locally square lattices or into locally, for instance, triangular lattices, and look at the influence of the interactions of the defects over different length scales and over different symmetries. So that is basically what is going to come next, and we are both working hard at this, both from our Swiss, let's say, partner, as well as the Korean partnership. And again, here, taking inspiration from what was shown to you from the previous talk, imagine that each of the colloidal particles that we can place in a specific position onto our substrate constitute the nucleation point for the various types of defects that Professor Yoon showed you before. And so I think here there's a lot of excitement in terms of what materials and what properties of materials we can fabricate and extract after we have control on the degree of, on the kind of defects, as well as on the position of relative defects. With that, I would also like to finish the presentation by acknowledging the people in my group working on this topic. We have a number of them that are working on capillary assembly, but in particular, there is Zazo, who's the PhD student hired through the Swiss-Korean collaboration, who's working onto the project. And as Dong Ki has said, this was the first instance of our mutual visits. So we had first the pleasure to host our Korean friends in Zurich, with the plan that we would go in June and be their guests in Korea, which unfortunately has not happened yet, but I really hope that this can happen soon and that we can continue with this collaboration. So thank you very much for your attention.
Thanks a lot, Lucio. It's really nice to see this kind of pictures where social distance was not an issue. Now it's really difficult to see the same, but I really hope that there will be the opportunity for you and your team to visit Korea soon. It's really an interesting country. So let's see. I think there is one question in the Q&A. Yes. So the question is for Lucio. Is it possible to make 3D assembly structure instead than a 2D planar structure?
Yes, under certain circumstances. So what we have been able to show, I think I messed something up with the screen sharing. So I seem to be monopolizing. Do you see anything on the screen? Just as
I see end of slideshow. Click to exit.
Okay, let's do this. Super.
It's going.
So I just wanted to show some additional. Yeah. So you see now the slides. Okay, so let me just go briefly to this slide over here. So the question is very pertinent and it's been asked. We got this question asked multiple times. So there's specifically two ways in which this can be done. So if you see these kind of triangular arrangements that you see over here, there is the possibility of tuning in a fine way the lateral dimensions of the traps, such that the three particles actually are a little bit further apart and they're not touching in the center. And that leaves an open space for a fourth particle to be placed on top by a fourth deposition. And we demonstrated that this is possible. So what we can do without altering the technique too much is to design the traps in such a way that there is the possibility of having some empty space that can be filled by an additional droplet as it moves over, by a careful design of the trap geometry and of the positioning of the particles inside the trap. But these are essentially, I would say, quasi 2D structures, in the sense that it's really not possible to build completely in the third dimension. To be able to do so, and we have not done it, but I see this is conceivable. What one can do is to do, let's say, a first deposition of the 2D arrangements that you would like to have, and then you transfer those particles into a substrate. You do another arrangement, and then you transfer those particles on top of the previous ones by aligning the two patterns. Let's say with a kind of mask alignment process like the ones that you would use in a clean room. And then doing by this, you could layer by layer build up three-dimensional structures.
Thanks a lot, Lucio. There are no questions, but I have a few. So for Donkey, how can you control the size of the defect?
Okay, actually, as I mentioned in the slide, it is the molecules have this kind of tangential alignment. So, which means in the thicker film, the tangential alignment happens slowly to make a bigger domain. If we make some thin film with liquid crystal, then we'll get this. I mean, for example, this and that size of the focal conic domain or Boojum defect. So it depends on the film thickness. As film thicker, I mean, as thicker film used in the experiment, we can get a larger defect. This sense?
Thanks a lot. Yes, the answers to my question. And about, Lucio, about the scalability of the technique, what is the scalability and how can you turn it into a production tool?
Yeah, so the way in which we make the samples now, it's made in the lab. So these patterns that you have seen in the presentation, they typically have dimensions of, let's say, 1 by 2 centimeters. And so this corresponds to a number of particles or a number of traps that goes, let's say, between 1 to 10 million, depending on the relative distance between the traps. And so that's sort of the scale that we can work with. And let's say making one of these patterns will take you maybe my students have a different opinion on it, but let's say the order of 1 hour, if everything goes well, of actual deposition time. So the way in which one could scale this up would be to do it in parallel, and that would also give you a certain flexibility in that respect. But the best way would really to be able to do it in a continuous fashion. And so to do it in a continuous fashion, the current problem is that we have a single droplet, and so after the droplet evaporates, you basically run out of material. And there would be, and there are already some pre-existing studies that show that you could have a sort of continuous feeding of the suspension from the top part of the chip, so that in a sort of a microfluidic type chip device, you have a continuous motion of the bottom template sort of on a roll, and this can then be a continuous process for the deposition. So this is not something that we do in our group, but if there's any interest in turning the process into an actual production, then I think that's the way in which one should go.
Thanks a lot. There is a question for Professor Yoon. So what interaction between the liquid crystal and the surface creates either the planar or homeotropic anchoring? And how strong is this interaction, for example, compared to thermal fluctuations?
Okay, it is the interaction between the substrate and the molecule. For example, in the normal condition, the molecules want to be aligned like this way. But if the substrate is treated with the low surface energy material, for example, fluorinated something or some normal, the self-assembled monolayer, then, as I mentioned, each molecule has aliphatic tails like this. Then, if the substrate, on the substrate, if it is treated with the arcuate tails like this, so they can be staggered together to make homeotropic anchoring. In normal condition, energetically, the molecules want to be aligned like this way with the van der Waals interaction or anything between, for example, hydrophobic interaction, whatever, but which is compatible with the thermal energy. That's why when it is heated over like isotropic temperature, the anchoring condition is erased to align randomly. So it is compatible with the thermal energy like KBT.
Thanks a lot. And for Lucio, are there any limitations on the material that can be partnered?
Yeah, there's not really. In the sense that what we showed, as I showed in the slides, that we can use a large variety of materials that go from kind of organic to inorganic materials, metals, and whatnot. And in our group, we are also currently using the same technique to deposit bacteria, so to deposit live objects. So the main restriction that exists here is the fact that these objects need to be able to be, say, colloidally stable in an aqueous environment. And so because the technique is based on the evaporation of water and the control of the capillary forces by adding surfactants to the system, and the materials that are used for the chip fabrication, especially PDMS, is soluble in oils. So the adaptation of the same technique to objects that are not dispersible in water, but they need to be dispersed into an organic solvent would require a change of the materials that are used for the chip. And we have not really worked too much on that, but the possibility exists. So to answer the question in short, sort of any aqueous suspension that is colloidally stable, so any material that composes a colloidally stable suspension in aqueous conditions can be used for the deposition, from metallic nanoparticles to colloids to bacteria. The switch to systems that are soluble in organic solvents would require a modification of the process and of the materials that are involved with the fabrication of the chips.
Okay, thanks. I have a last question. So it's for Donkey. What are the possible applications using defects of liquid crystal phases?
Basically, the defect core has a greater energy than the other places, which means they can, the energy, the free energy near the defect should be stabilized by trapping something. So sometimes the defect core is used to trap the other material. Even small molecule like a chemical dye can be trapped in the core of the defect. So I think when our group and Professor Isa's group collaborate together to make addressed cores, address the defect cores, then we can trap the other material in the core. And then, as I mentioned, the defect structure in the smectic phase has shorter ordering than the nematic phase, which means if we make some sparse patterns in the nematic phase, then we can fabricate densely arranged the defect structure in the smectic phase. Then multiply the particles can be trapped in the core of the defect in the smectic phase. Then the patterns can be doubled or multiplied by many times. So this is our strategy to use our defect structure with the Lucius pattern.
Thanks a lot. Actually, we really look forward maybe in 1 year to listen again to you and see, if there were some developments in the projects and follow this cooperation. For us, it's really important. So I think there are no additional questions, so we can slowly go to the conclusion of the Science Club. First of all, I would like to thank the speakers for your time and for having delivered such interesting presentations. As I mentioned, we really look forward to follow this project. It's in the goal of our office to sustain and support the Swiss-Korean cooperation, and we hope that Lucio's team can soon visit Korea, and also us, as we are based here in Seoul. Our team organizes this kind of activity quite frequently, so everyone interested can follow them through LinkedIn. And if there are questions or interest also in delivering some presentation or try look for partners in Switzerland and in Korea respectively, please send us an email at the address here in this slide. Now, before saying goodbye to all the participants, because and thanking them, I'd like to take a screenshot with the speakers as a memory of this moment. As we can't meet, at least we have a picture. So please smile.
Say kimchi.
Kimchi or cheese.
The same, cheese.
So done. Okay, so she's Jihan, and she's also a member of the team and the main organizer for the Science Club. So thanks all, and hope to see you, or at least having you among the participants to our Science Club soon. Bye bye.
All right, thank you very much. Bye bye.
Thank you.
Bye.
Bye.